Problem 2305, fair distribution of cookies. Start with the problem. We have two inputs. One is cookies and the other is K. Cookies is expressing the number of cookies in each bag of cookies we have. So we have one bag with 8 cookies, 15 cookies, 10 cookies, and so on. K is the number of children that we want to distribute this bag of cookies to. And we have to distribute everything to the kids. There is no cookies that don't belong to any kids. And then, now the question is, what is the minimum unfairness of distribution that we can achieve? So what is the optimal distribution by minimizing unfairness? Now, what is unfairness? Unfairness is the maximum number of cookies that a children have in a distribution. So, for example, in this example 1, the optimal distribution is to give one kid 8, 15, 8, and the second kid 10 and 20. And the unfairness here is the maximum number of cookies that the kid have, which in this case, this kid has 31 cookies, while this one only 30 cookies. So the value of unfairness for this distribution is 31, and that is the minimum. And that's what we need to calculate. So that's the problem. Let's see about the constraint. So the good thing here is that we only have at maximum 8 number of cookies, and the number of children is guaranteed to always be less than the number of cookies or equal bag of cookies. Okay, so it means that we guarantee that its children definitely going to have at least one bag. Now let's talk about the tactic to approach this. Okay, so we have cookies as a problem, and another one is the number of kids. Let's say we have the number of kids 3, and we have the cookies 1, 2, 3, 4, 5. Okay, so the brute force straightforward way to solve this is actually to just this to find all permutation possibles to distribute the keys, and then find the one with the minimum unfairness. Okay, and then let's try to go through that, and let's find what we can optimize when we are trying to do that. So what the permutation here means is, for each cookies, for example, it means we can give it to one of the 3 kids. Let's reflect it in an array. Because we have 3 kids, it means we have 3 values in the array. And these values actually reflecting the number of cookies that the kids have. Currently, it starts with all 0 because nobody get any cookies yet. So how do we do this? So one way to do permutations, of course, we go through the bag of cookies one by one and decide which kid actually get the bag. So let's start from here. So the first bag has 1 cookies. Whose kid's going to get it? It can be the kid A, the first kid, second kid, or third kid. And the thing here, it doesn't matter, because what we are looking for in our calculation is about the distribution. So distributing this first bag to either of the kids, the 3 kids, is the same. This is the same distribution. What it means is 1, 0, 0, 0, 1, 0, and 0, 0, 1 are all the same kind of distribution. All these 3 have the same level of unfairness, the same level of how the distribution can grow into. All of this has the unfairness value of 1. So this is where it doesn't matter. So as we can see here, the first bag can be distributed with to any kind of kids, and that won't change our distribution result. Okay, then the second back number 2. So back number 2, for this one, we can give it to kids number 1. We also can give it to kids number 2. We also can give it to kids number 3. But look at this. Giving it to kids number 2 or to kids number 3 is not having any significance to the distribution. It's distributed the same way. The unfairness value is the same. At this level, the unfairness value for these two both are 2. This one will have the unfairness value of 3. Remember, the unfairness is the maximum number of cookies that the kids has. Okay, so this is another pattern that we can see there a pattern of things that we can save here. It means that as long when we look at the cookies index, as long as this is the cookies that has less than the values of the number of the children, we only need to look at that maximums of the cookies. So for example, what it means in better wording, that might be a very confusing word. It means that the boundary we need to look at, like until it doesn't make any new distribution significance, is the minimum of the cookies index plus 1, because cookies index starting from 0, array index is starting from 0, but if you remember the way we go into it, the first index, which is index number 0, we only need to look at the 1 kids, and distribution to the other 2 kids doesn't matter. It doesn't change the distribution. While when we look at the second cookies, we can distribute it and have a different distribution when we distribute it to kids number 1 and kids number 2. That's why it's cookies index plus 1. Okay, and then it's a minimum between that and the number of kids, of course, because that's the maximum you can. The maximum number of way you distribute a certain bag of cookies is of course those 3 kids, because we only have 3 kids. That's why the number of kids or the minimum into the cookies index plus 1. That's the maximum we need to look at when we are distributing each bag of cookies. Now, once it goes into the third one, at this time, we need to look at the possibilities of all the 3 kids. Okay. What it means for the first one, it means we need to look at if what happened if we give it only to the first kid, and then if we give it to the second kids, and then when we give it to the third kids. Okay, and then the 1 to 0, this one the same, whether we need to give it to the first kid or to the second kid or to the third kid. This all give different distribution. Okay, so that's about it. And then once we already go through the list, we just need to went through all of the permutations. So the saving we can get is when the cookies index are less than the number of children, then we can easily cut down with this simple rule of checking the boundaries of permutation we need to go through. So that's was saving, and that's how the permutation basically works. And for each combinations, once we already go through all the cookies, what we need to do is just simply to calculate the minimum unfairness out of all possible things. Okay, so that's basically the descriptions of how we are going to do things. Now let's do it. First of all, as can be seen here, we need to express the children holding cookies by this array. Let's call it simply as the children array. And it will start with all 0 value for the k number of children. And for each permutation, of course, what we need to do is we need to do a recursion. And what does our recursion need? Our recursion need the cookies, right? And it also need the index of the cookies that is being looked at the moment. And then it of course need the children. It also need regarding calculation of unfairness. Remember, the definition of unfairness is the maximum value of the kids, that the number of cookies that the kids have. Okay, so in order to help doing that, for each iteration we can simplify it. We can bring over what we calculated before by remembering what was the maximum before. Okay, and then comparing it only with the one we changed. So for example, when we go from here to here, it's as simple as going through what was changed before and what was the value, the maximum before. The maximum before was 1, the change 1 become 3, maximum of 3 and 1, the unfairness become 1. Another one is this one. So the maximum before unfairness is 1, and then if we make the changes here, the new changes is become number 2. Now we compare the maximum 1 versus 2, so the maximum unfairness, the unfairness become 2. So that's why we need to remember about unfairness so far, or previous unfairness. Yep. So how are we going to do the recursion? To do the recursion, we simply need the termination condition. When we do terminate, remember we finish the thing and start comparing with what was the minimum unfairness we can get out of all permutation we have. When we already go through all the cookies, we go through all the cookies when the cookie index is equal to k, not k, length of cookies. Okay, at this point, this is our termination condition. And what do we do when it is in the termination condition is actually to find what was the minimum. Let's have this as what we're going to return in the end. Minimum unfairness, at first, of course, the worst could be is the sums of all the cookies. It means one kid has everything. Okay, and when we go into termination condition, we just need to check whether the new unfairness is actually lesser than the previous minimum unfairness. Okay, otherwise we do, this is the part where we do the logic of the recursion. Remember what we do just now? For each cookies, because this is actually a function that is called for each cookies. For each cookies, we're going to go through the minimum of either the cookie index plus 1 or all children and try to push in the cookie base to each of these possible children. Okay, so it will be a range between the minimum of cookie index plus 1 or k, the number of children. And what we do is we give the cookie to the corresponding children. So what it means in code is children for I here is actually the index for the children. Okay, for these children we try to give the kid the cookie, which is cookie index. Okay, once we give the cookies, we need to further do that iteration but for the next cookie. So we pass almost everything except the cookie index will be the next cookie, and the previous unfairness for the next iteration will be the maximum of either the previous, compare it with the children that we change. That become the next previous unfairness value. Okay, after that this will be doing like a depth first search, and then once it's terminated, we already done with that permutations. We will tag the cookies back from that kid to give it to another kid. So here we change it into minus, and there it goes all and all and all until we all get all the possible permutations and get the minimum unfairness. Let's try this. So wait, what? The answer is wrong. Expected is 31. What is wrong here? Is this the right one? Yep. So somehow it's over by something. Children child index, minimum cookie index plus 1 compared to k. Oh, of course, because we haven't called the function we created. So it will be starting with the cookie index 1, and it will start with the previous unfairness also 0. Okay, so 0 index of the cookie and also the 0 unfairness because we haven't give any cookie to anybody, so no unfairness can be calculated yet. Let's run the examples. Now it's giving the right answers. Let's submit this, whether this is fast enough. Yes, it's fast enough. So this efficiency we do here, so this is actually the efficiency we create, this one line of code. This makes it acceptable. Let's convert this into removing the efficiency, which is just try to give it to all the kids. What happened? Will this be accepted? It's quite slow. I think it will be rejected. It is rejected. So you see, the essence of this to solve this problem is in this one line at number 19. Okay, now let's try to calculate the time complexities. This one is a little bit tricky. So children 0 times k, so of course this is big O k. Minimum fairness, this is just big O1. Recursion, this is the tricky part. Okay, so in this recursion, all of this is just assignment comparison, is all just big O1. This is the expensive part. This for loop means big O minimum of either cookie index plus 1 or k, right? Cookie index plus 1 or k, okay? And then at this one, it will recurse into for each of the cookies. So if we can imagine it, it will do recursion for each of the cookies, right? So the number, the length here will be length cookie, okay? Now, how to do this, how to calculate the time complexity is the fact that that's what happened. We need this recursion will recurse for each of the cookies. It will do the depth until the depth of all the cookies, right? But the for loop here will only will choose either goes to k or cookie index plus 1. So what happened here, let's imagine if this is just simply k. What it means is we do k for each length of cookie. Let's say length of cookie is n. This simply means, if this is what happened, it simply means k to the power of n, okay? But because we do this efficiency that it will choose the minimum between the cookie index plus 1 or k, it means that it will do this for the first few until the cookie index is equal to k. Then after that, it will start to become k, 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 k. So the normal permutation, if we permute everything, it will be k to the power of n, where n is the length of cookies. But when we do this efficiency, what we got, 1, 2, 3 until the cookie index is the same as the number of children. It means, if you remember this in mathematics, it is a factorial. So it will be k factorial at the beginning, okay, until it reaches the k. After that, it will do the k times k times k times k. So it will be k to the power of n minus k, because the first k will create a factorial, which is much more efficient than exponential. This is exponent, all right? So this is what happened when we do this. So that is our time complexity. Maybe let's do this, okay? That is our time complexities. And this is the more expensive one because this recursion is actually doing factorial and combinatorial and exponential, while the rest is just what, big OK, big O1. So when it's sequential, we took the largest, so this is our time complexity. K factorial times k to the power of n minus k, and that is smaller than k to the power of n. And we proved it just now when we compare the run with this, compared it when we replaced it with a simply k. Okay, so that's it for today. And we can see here one line of code changed the performance in quite a bit. Thank you for watching.